Yeah, I mean,
Thursday plus 4 minutes.
a drag factor.
Oh, I kind of don't.
Really? So you're getting more early.
I get more early.
Huh.
Well, also because I had things, you know.
Yeah. I keep trying new ways to get here, so sometimes it takes me longer.
Yeah, so
This time I did a new creative way.
You're late.
Yeah, I'm late. So it's probably a couple minutes longer.
Okay, so good morning, everyone, and welcome to the first session of today's workshop. So our first session will be by John Owens. He is a professor from the Department of Electrical and Computer Engineering from UC Davis. And John Owens is a pioneer in fundamental algorithm and data structure in GPU computing. And I'm looking forward for your talk. Thanks a lot.
Good morning, Mike. Cool. Okay. I'm excited to be here. Coming to an audience of theorists is always really exciting because some of my favorite work that I've done has been getting to collaborate with theorists. And I am by no means a theorist myself, but I learn a lot from all of you. And I think there are really wonderful collaborations with people in our community. Just as a trigger warning, some of the things that I will say from a theory point of view are going to make you feel kind of creepy because we do some things that you're going to say, holy cow, that is like so far off what we should be doing. And some of these things we do for good reasons, but you might even have better reasons we should do them in a different way. So as I've talked to people and seen these talks, I came here thinking that this talk would be all about like the details of doing dynamic graphs, but and how we do them on GPUs, but I'm going to say that's actually a pretty small fraction of the talk. The picture that I'm getting is it's going to be a better opportunity for me to give maybe a little bit of a bigger picture about the way we think and some of the constraints we have so that you understand where we're coming from and that maybe we can have some of the same vocabulary. So the data structure kind of stuff that I have done has been in collaboration with theorists. Our group built the first the first hash tables that could be built on the GPU, and that was a cuckoo hashing construction. And then more recently, I've been collaborating with Martin Farish-Colton, and we've done a lot of the first dynamic data structures on GPUs, and that's relatively recent work, and we've built a whole bunch of stuff, and I've really enjoyed these collaborations. One thing that I really want to point out on this slide, though, is that when we look at sort of when the work was done in the theory community, when cuckoo hashing was first described, and then when we actually did it on the GPU, or when bucketing, for instance, as a hash table technique was done, versus when we were able to put it on the GPU, there's a big time gap there. I mean, it takes a while for your great ideas to percolate into our community, and that's why I really want to emphasize there's a lot of opportunities there. I'm excited by some of the stuff that I've seen this week, and I think you should feel open to tell people in our community, hey, these are really exciting things that are happening, and what does this look like on your kind of platform? So I want to note what's different for me as a systems person than you as a theorist. Like, what do we think about when we want research contributions? And probably the number one thing is we want to build something, and then we want to evaluate it. And how do we evaluate it? And your evaluation is like, well, we had this bounds and we made it better, or we had this bounds and we made it tighter. And it's a very cut and dried kind of thing. For us, we kind of have different goals. We're less interested in the theoretical running time as we are in the actual running time. And so we try to make things faster, and then we try to do things that couldn't be done before. But for us, I don't want to do work that is a solution in search of a problem. And there's a lot of research out there that is, well, I built this thing, but I don't really know what it's for. And so we're actually really trying to, we believe that systems work can be used to solve real problems. There's a lot of good real problems out there. So we look for both problems and data sets that people care about in the field. The other thing is there's a lot of systems work out there, at least that I review, and it's a little bit frustrating when it's like, I did this. It's like, I built this thing, and here's how I built it. And that is not really what we want to see in our community. And just to note what we do want to see There's a really wonderful post by Kayvon Fatahalian, who's a professor at Stanford, and we overlapped in grad school, which is kind of fun, really, really sharp guy. And he talks about the characteristics of good systems papers. And the things that I really want to emphasize are, one of the important things is to say, hey, we built this, but here were our choices. Okay, we could have done this and this and this, and we tried this and it was a bad idea. And we think this is a bad idea, so we didn't pursue it. And this is why we got to where we are. Equally important is constraints, to say, here are the constraints on our problem, because then somebody can come back and look at your design decisions and your constraints, and maybe those are different in their scenario, but at least they can see what your thinking was and build on that. And it's just much more important than I built this. So how do you get started as a theorist starting to think about this? If you can come and say, look, here's this problem of practical interest, that's something that we really love to hear. And I think you know all these things, and I'm hearing all these data structures and like constructions, and like they're really complicated, and most of what you know is not known to our community. So if you come in and say, you know, this work was really exciting that we did, and is this something that we can, you know, put into practice? There's this other work that's out here, and like everybody's excited about it in my community. This is maybe something that, you know, again, could be put into practice. And then to sit down and sort of think about what the constraints are. Well, turns out if we use this technique, it really requires X and Y, and that's not great for your target, but there's this other way to do things, and it only requires Z, and maybe that's a good. And so those are the sort of conversations that I have when we get started talking to theorists. But I do want to emphasize like the gap between all the wonderful, beautiful algorithms and data structures that you build and what's actually been put together in the field and what's actually being used is large. And I really do think there's a lot of opportunity. Okay, so I'm going to spend the next little bit sort of telling you how GPUs work at a high level. And so some of this is just to introduce some terminology, but just to say how we think about problems. So what does this machine look like that we're looking at? So this is sort of the one slide. What is the programming model for, in this case, NVIDIA's CUDA. And it's sort of the dominant way that you program GPUs, but there's other fairly similar interfaces that can be done. But generally what you do is you start off with a CPU that has a lot of data on it, maybe attached in a disk, maybe in the CPU's memory. And you take that data and you move it over to the GPU. And then you call what are called kernels on the GPU, perhaps this series of kernels, and it's going to operate on this data. And the GPU has its own memory, right? So it's got this really big, not really big, has a relatively small, very fast, fairly expensive memory, and it does all of the work in its own memory. So it'll churn through this for a while, and then when you're done, you take the data and you bring it back. So it is a coprocessor, and it's under the direction of a CPU. So what are these kernels? Like when we do compute, what does that actually look like? So we call a kernel over a grid. And so a grid is 1, 2, or 3-dimensional. You get to decide as the programmer. And it's a grid of blocks, okay? And each block is, again, something that you get to define in terms of the dimensionality and size, but it's a group of threads, okay? So grid is a grid of blocks. Block is a big group of threads, right? And so each thread knows its identity. It knows how big blocks are, how big grids are, and so on. So it's a little bit like a PRAM kind of model, because what you're going to do is you're going to write one program that runs on one of these threads, and the hardware will run the same program on every thread. And so they can cooperate in interesting ways. And the distinction between having this little 2-level structure of grids to blocks, blocks to threads, is that threads within a block can cooperate in a way that threads across blocks cannot.
Are there some strong restrictions about this same program assumption? Like, you can always say the program is, if I'm thread 0, run A, if I'm thread 1, run B. And again, like, in principle, you could maybe drop this, but is this maybe enforced in a stronger way?
Yeah, so the question is, could I have, we think about taking the same program and running it on every single thread. What kind of differentiation can we do between threads? And so, yes, you can absolutely write a program that says every thread with an odd ID do this, every thread with an even ID do this. The programming model there is called SPEMD, single program multiple data. Now, there's some efficiency issues with that, but absolutely you can have branches in that program, and those branches can be based on which thread or block or so on.
So threads within the same block can cooperate, others cannot, but what do the grids get you?
Right. So the question is, threads within the same block can cooperate. Blocks are independent. The grid is the overall data structure that says this is the number of blocks that I have and their dimensionality and span. Okay, so you launch a kernel over one grid. That grid says, hey, I've got a bunch of blocks, and then each block has a certain dimensionality. There's lots of restrictions in here. So for instance, you can't have more than a fixed number of threads within a block, right? So it's not arbitrary. But what this says is that threads within a block have a lot of locality and can cooperate at a very fine-grained level. Does that answer your question?
So grid 1 and grid 2 is just parallelism.
No, this is grid 1 and grid 2 is just parallelism. No, kernel 1 will launch over a grid that it specifies. Kernel 2 will then launch over a different grid. This is a computational structure. It's not a data structure. It's just saying I'm launching 1,000 blocks, each of which has 1,000 threads in it.
But I mean, we are trying to solve one problem with multiple kernels, right?
Perhaps, yes.
So why do I have an advantage of using multiple kernels versus using one kernel with many more blocks?
They could be sequential, like, hey, I have to calculate this thing first and then calculate this thing second, and this grid need to be different dimensionality because of your problem. It might be that it makes more sense to fuse them out, like that's a fission kind of problem, right? Like a compiler sometimes will split into this. So, if your mental model is, I just call one giant kernel over this huge grid, that's totally fine. But we have the ability to do multiple in sequence.
Thank you.
So I know maybe you're getting to it. The synchronization, where does the synchronization occur?
Where does the synchronization occur? Okay, so there is an implicit global barrier between kernels, and that's another reason you split things into kernels. So it basically says everything here must finish before it does here. Within a block, you can call a barrier synchronization. Okay, so you can say all the threads need to arrive at this place before any of them move forward, and that is a low-cost thing to do. A global barrier is pretty expensive, but within a block, you can have a synchronization. Then you have I say that these need to be independent, and they are. They can't be dependent on each other in the sense that this can't be waiting for this to finish because they can run in an arbitrary order. But you can do things like atomics that these share. So he could be incrementing a counter while she is checking a counter or incrementing it herself. Does that make sense? Okay.
So I'm still confused. So you say it's a timeline. So kernel 1 finished before kernel 2. They're not in parallel at all.
So right. So could I launch multiple kernels in parallel? Yes, I can. There is capability on the hardware to do that. There are reasons to do it, but in general, the normal way is to say run this, then run this, because there's not really an advantage in running two of them next to each other. Like all you're doing is splitting things in space instead of time. So it is straightforward to be able to write code in this way, and people think in a sequential way. But there is ways to have multiple things happening at the same time.
Just to clarify then, these do not represent different chunks of the hardware. These are
So do these represent different chunks of the hardware? So I'm going to show the hardware on the next slide. This represents this kernel using the entire hardware to run over this grid. And then this, this finishes, everything's done. And then this uses the entire hardware to do it again. Okay.
Good.
Okay. So cool. So this gives, we have a lot of parallelism here. Okay, we have parallelism across blocks, and blocks can run in an arbitrary order. There's no enforcement on that by the hardware at all. And then there's parallelism within a block. Okay, and so your mental model is that you literally have hundreds of thousands, millions of threads in flight at a time. And in fact, the latest hardware, and I'll show the stat in a little bit, is that to keep the hardware busy on the latest GPU, you have 300,000 threads that are literally in flight at any given time, like are in registers. So that's a lot of threads. There's a lot of stuff happening at the same time. And the programming model exposes that by letting you express parallelism across blocks and across threads within a block. Okay. So the thing that I want you to take into the next slide is there's parallelism across these blocks. Okay. And when we launch a grid, we're saying, hey, here's this big collection of blocks. And then the hardware has cores. Okay. And they're called SMs, streaming multiprocessors. And in this case, this GPU has 144 cores. Okay? So the job of the hardware, the primary job of the hardware is to take a block and assign it to a core. So you might launch a kernel that has 10,000 blocks in it, and then the hardware is responsible to dealing those out to cores. Okay? So every time a core becomes idle, the hardware will give it another block, give it another block, give it another block. Hardware's really good at this. It keeps the hardware busy all the time. And if we go back a slide, the right way to think about what a block is it's a virtual core, right? Your mental picture is, if I want to launch 10,000 blocks, I think about having a GPU with 10,000 cores. There's only 144 cores, and the hardware sort of de-virtualizes that. Okay? So what that makes, because these blocks are independent, they don't depend on each other, it means that you can take a program you write here and run it efficiently on a GPU that has 2 cores or 144 cores. And it'll just run faster if it has 144 cores. If you've exposed enough parallelism within the program, then it will run efficiently on large or small GPUs. And that's really the biggest thing they tried to do with this programming model. There's a lot of explicit parallelism, but it scales nicely.
So how about shared memory and stuff like that?
Okay, so I will talk about the memory system. I will talk about it here. So let me tell you what's in each of these cores, right? So this is this big GPU. If you want to like hoard things right now, this is a really good thing to do. They're extremely expensive and hard to get, like because they're in enormous demand. Everybody wants them in their data centers. NVIDIA's making scads of money because they've done a great job building these GPUs. So what we have here is 144 cores. This big blue things here is a level 2 cache that is shared among all of these cores. And then there's a memory interface that goes out to DRAM, and all of them share the same memory interface. So they have one pool of DRAM that's outside here. Okay. There is an enormous amount of compute here. So, double precision or single precision floating point, dozens of teraflops, okay, which is a ton of flops. If you are doing specifically deep learning kind of math, and you can structure your stuff in like little 4x4 dense matrices, then you can get an order of magnitude more because there's special purpose hardware to support that. There is, on the highest end GPUs, 80 gigabytes, and that's relatively small compared to what you can get on a CPU amount of DRAM, but a really high bandwidth to that DRAM. They use HBM, this high bandwidth memory. It's small because you need that to make it run fast, but that is a lot of bandwidth. And then they're gradually adding new instructions, new hardware to be able to do cool stuff. So in this latest one, for instance, there's hardware to accelerate dynamic programming that they say will has a 7x speed up over the way that they did things before. Okay, so what's actually in each of these cores? So I sort of zoom in on that little core here, and here's what it looks like. And so what it is this giant sea of floating point units, okay? And it has integer math as well. But you're gonna see each of these little boxes is a different ALU. There's a whole bunch of 32-bit, a whole bunch of 64-bit. This is integer math here. There's this big register file, which I'll talk about in a little bit. There is hardware that does this tensor operation that's really optimized for deep learning training. And then there is a pool of cache. Okay, and so this is the next part of the memory system. We have a pool of cache here that's shared within a core that can be used as basically a scratch pad memory. So you can either use hardware supported like level 1 style cache, or you can configure it to be just a big array that you get to manage any way you want. Okay, so you literally declare an array and you get to populate it. Okay, and that's shared by all the threads within a single block. Okay, that's the hardware. Look, there's lots of stuff in it. It's giant. And it's a lot of fun to program because you just have an enormous amount of compute at your disposal.
Is it even possible, maybe I can do it offline, but just is it possible to say that some of it is an array that I can control and some of it is left for cache?
Yes, so the question is this 256 kilobyte L1 data cache / shared memory, you get to sort of draw the line between that. So you don't get an arbitrary place to draw that, but you do get to, there's some places where you can say, make this mostly L1 or make this mostly the shared memory that you can configure. Okay, so just to look at the memory system, because this is kind of wonky compared to, I think, traditional CPU memory systems where you have sort of this, things as you go farther away get much bigger and much slower. So first we'll look at the memory. So global memory that all threads can access, okay, up to 80 gigabytes, which is again pretty small compared to the CPU world. You can buy a CPU with like a 5 terabyte memory system. So this is a big limitation. Then we have a big pool of shared L2 cache, okay? Per block, okay, within a block, you have 256 kilobytes, and so you can configure that any way you want. And so if we aggregate that over all the SMs, that's 36 megabytes of cache. So you look at this and like, this is only a little bit smaller of L1 than you have in L2, and that's not typical of the CPU memory system. Warps are something I'm not going to talk about right at the moment, but then we have registers, okay? And that's a lot of registers. The idea to have dozens of megabytes of registers is very strange, right? With 30 megabytes of registers. The reason for this is because if you want to have a lot of threads in flight at a time, okay, then you need to be able to store those threads. And so the fundamental thing that a GPU does different than a CPU is that a CPU will try to minimize latency, right? So there's all these things on a CPU that minimize latency, like branch prediction or caches or value prediction or tons of little things, out of order execution and so on. They're trying to minimize latency as much as they can. GPUs tolerate latency. They say, you know what, we've got this long latency, so we're going to run until we stall, and then we're going to switch over to another thread and run until we stall, and switch over to another thread and run until we stall. And by the time we're done with all those threads and we get back to the first one, hopefully that long latency operation has completed. Okay? The only way you can do that is by having lots of threads in flight at a time, so you can switch. And it's very efficient to switch between threads, but it means you need this giant boatload of registers to be able to make that work. Okay? So that is just a get-out-of-town amount of registers. Okay.
This is storage that the system needs, right?
This is
Storage that the system needs. The program that executes can't really use it.
So the question is, does the system need all these storage? It's saying that if I launch 300,000 threads, each of those threads is resident, can run on the next cycle, it means that I need registers to be able to store them. So when we look at this big block diagram, this register file, this block here, physically, it's very large, and it's able to store, within a core, 2,000 threads in flight at a time.
But can you, if you don't have as many threads, could you use it for other things? I mean, I'm just,
Sure.
as a theoretician, immediately say, well, why don't they make it twice as big so I get some registers as well for my program? And
Yeah.
don't waste them.
So,
Things are not as paralyzed.
so the question is, could we use them for something else? So yes, they're only accessed as registers, so you don't get like indirect access to them. That's maybe more detail than I want to go into right now. I'm going to say that registers are often a precious resource. So, if I want to fill the machine, then every thread gets no more than 32 registers, which is not a lot. Okay, but yes, we do try to use them for all sorts of creative things. And we do a lot of thread coarsening where we say, oh, this thread should run 2 or 4 or 8 things, and so that'll take more registers as well. But that's kind of an offline question.
Okay.
Yes?
Is there an issue of fault tolerance here? Like, do pieces,
Fault tolerance.
Yeah, does fault tolerance come up with all those threads? Is that, I mean,
So I'm going to say short answer, no. Long answer, maybe a little bit in the sense that NVIDIA will turn off some of the cores if they're broken in any way. So if you go buy a cheaper GPU, it's a more expensive GPU where some of the cores failed. But I'm not aware of like dynamic things that are like that. So, okay. Cool. The other thing I want to mention briefly is this computation hierarchy here. And the thing that I really, we talked about kernels and blocks and threads. The thing I really want to mention, though, is this idea of warps, because this is important. So the actual atom that gets run in here is 32 atoms that are in SIMD lockstep. Okay? So every time it issues an instruction, what it's issuing is 32 threads that are all running together. Okay? So it's called a warp. You can think of it as 32 wide vector. Okay, and that thing runs in lockstep in the sense that if you want to branch, then it can't run both sides of the branch at a time. If you say even threads do this, odd threads do this, what's going to happen is the odd threads run and the even threads are asleep, and then it switches. So it's important to make the most of the hardware to try to minimize that divergence. And we spend a lot of time trying to craft algorithms so that it does minimize that divergence. And then some workloads, this isn't a problem at all. If you're doing dense matrix multiplication, everything's sort of doing the same thing. But the workloads that have the most throughput minimize divergence here. But this warp is important. Okay, so what matters when you're thinking about doing computation? Okay, so the most important thing is filling the machine, right? This machine can have 300,000 threads and flight at a time. If you're only launching 50,000 threads, most of your machine is going to be idle. So we need problems that will allow us to be big enough to have a lot of threads, and I want to keep those threads busy all the time. We want to avoid divergence in compute, especially at this SIMD 32 neighboring threads level, right? If they're all branching in a different direction, if 32 threads all branch in a different direction, we have a 32x slowdown there. Contention turns out to be pretty important. Like we see data structures that don't think about contention at the scale of hundreds of thousands of things banging on a lock at the same time. And so we did some work on building up B trees. And when we took just sort of this normal, like classic B tree thing, compared it and implemented that on the GPU and compared it to how we did it when we implemented it in a very GPU-friendly way, that was a factor of 1,000. And it was mostly because of contention, right? Just we had lots of threads waiting for other threads to finish. And so thinking about problems at this scale of concurrency is not something that's traditionally done in the CPU world.
Sorry, what is contention again?
Contention meaning like I've got a lock, okay, or latch or whatever it happens to be, and only one thread can own this lock or latch, whatever at a time, and a bunch of other threads are waiting for it. So when that's the case, you're sitting idle, you're not doing anything. So we try to design things to minimize that.
Just to clarify, you took a standard CPU implementation, ran it on a GPU?
No, it's not like a single threaded thing. We took a design that would be sort of your textbook B tree, and said, this is how you do it. This is your latching strategy. This is when you split nodes and so on. And then we implemented that. And then we said, okay, now let's think about how to do this in the GPU. And there was a lot of, hey, we'll give you extra, we'll trade computation for contention. We'll do extra computation to avoid contention.
Okay, so you kind of implemented a relatively straightforward fashion, but on the GPU
Yes.
as a baseline.
In a parallel way.
In a parallel way.
Right.
Okay.
Do you have like atomic semantics similar to what a GPU offers?
CPU, yes.
And then if so,
We have
do you-
atomics, yes.
And then do you think that a concurrent data structures that do not use any locks may translate in a nicer way to a GPU because of that?
I don't think they're appreciably different. Like, I mean, we're not implementing these in this weird GPU way, like our locks look like your locks. But if you have 299,000 threads banging on them, then that's a lot of loss of concurrency.
So basically you're saying that concurrent, like the data structures which are concurrent by design may be GPU friendly, right? Is the
Yeah.
Okay.
Yeah. But even then, there's a lot of algorithmic engineering involved in taking a CPU B tree design and making it more GPU friendly. We got a really nice paper out of this. And I think what we learned about concurrency is broadly valuable. Okay. Cool. Memory-wise, we spend a lot of time, and I'm sure you do too, thinking about how you can use the lowest levels of the memory hierarchy or the closest levels of the memory hierarchy. One thing that's very important, and this is not GPU specific, but it's DRAM specific. When you touch a line of DRAM, basically you're paying the cost of, I touched one bit in that line, I've paid for the entire line. That's the way DRAM works. What this means in terms of how it's implemented on the GPU is if you've got 32 threads in lockstep and they all go out to DRAM at the same time, okay, and they all touch the same line, that's the same cost as if one of them touches one word in that line. Once you touch that line, you've paid for the whole line. So you really want to structure your memory accesses so you've got a whole warp accessing things next to each other. And then that's how you get full bandwidth. And we call this coalescing. And this is somewhat similar to the external memory model. One thing that doesn't really used, at least in our community, and maybe you can help us use it better, is L2 cache, this global cache, which is really big in the sense of like really using that efficiently. And the reason is because if you look at the number of threads you run on the CPU compared to the amount of L2 or L3 there is in a CPU, each thread kind of owns tens or hundreds of kilobytes, right? There's a fairly large working set that each thread gets, because you've got 32 threads maybe running on a CPU, like everybody gets a fair amount of space. When you have 300,000 threads running at a time, even with a 50 megabyte L2, you're only having a few hundred bytes per thread. And it's harder to take advantage of what is really a very small thread allocation. So the places where we've seen this be useful is when all the threads need the same thing, right? So in our B-tree implementation, it turned out to be nice because B-trees should be good in terms of taking the upper levels of the B-tree, storing them in cache, and then lots of threads want to access them, and it turns out that worked in practice. But most of the time, this is so small that we don't really get to take good advantage of it. Okay, so I don't know models like you guys know models, but here's some of the things we think about. GPU DRAM is relatively small. You probably think about external memory models being with more memory, and we don't do a lot of work beyond GPU DRAM. Most of the work when we scale to multiple GPUs is honestly that we say 80 gigabytes isn't enough, so we're going to use 8 GPUs because that multiplies the amount of memory by 8, which is kind of a crummy way to do it, but that's what we end up doing. And there hasn't been a ton of at least interesting academic work in terms of how do we extend this to CPUs and disks and so on. But it is like the external memory model in terms of how we access DRAM, this idea of coalescing being really, really important. And it turns out most applications in the GPU world end up being bandwidth bound. There is so much compute here, right? It's hard to build something that ends up being compute bound because we have so much compute.
What do you mean by limited work to extend memory hierarchy to CPUs?
I'm saying like that seems really important, and I don't think there's a ton of academic work out there that does like, oh, here's this interesting insight about how we can use the CPU as this backing store and use disk and so on. Like, there's not a lot of GPU specific work there. So there's good systems support for having a unified memory system and doing automatic paging, but it's not something academics have really touched. And if there's good ideas that we could have there, I would love to hear them.
So you mean the combination? You mean the combination of CPU and GPU?
Yeah.
Okay.
Or CPU, GPU, and disk, or CPU and GPU, and like there's a lot of practical things that have been done. I just haven't seen a lot of like, oh, here's this really great idea that academics came up with. Okay. And then finally, like, I get asked all the time, like, oh, I want to build this GPU thing. I don't really know much about GPUs. What's the model I should use? And the problem is, it's really complicated to program GPUs well. There's so many things you have to juggle. There's all these weird corners. And so, like, every time people say, oh, I'm going to use this model, and I say, well, it doesn't account for this, 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 or this. And the intersection between, like, things and things that I find useful ends up being, like, really small. And it's sad. And it's our fault because we built this really complicated GPU. But I don't have a good answer when people say, like, what's the model that I should think about, which is unfortunate. Okay? And I don't know that there's a solution for this problem. It isn't like there's this magic model out there that takes into account all the things we think are important when we write programs. Okay. All right, now I'm going to talk just a little bit about sort of how things have changed over the last few years, and this is going to get to graphs eventually, I promise. So I've only had one sabbatical where I went and did something cool, and that was in 2012, and I worked at Twitter for 6 months, and it was awesome. And I spent a lot of my time saying, look, you've got all these big complicated pipelines, and they all run on the CPU, and maybe there's this thing we can do in this pipeline that's like on the GPU, and it's like a lot faster than you can do on the CPU, and maybe you could think about moving it over. And this was a really hard sell to make because none of the vendors had like GPUs in their data centers in 2012, okay? And the problem is that this has this really fast memory, but the pipe between CPU and GPU is slow and still remains slow, right? So the ones that we have in our like cluster are like 32 gigabytes a second. And I've got way faster than that. And so it means that if you're gonna move something to the GPU and do compute, it better be way, way faster, okay? It is faster for us to do a BFS on a big graph than it is to transfer that graph from CPU to GPU. Okay, like that's just the reality of things. It's a really, really slow pipe. Okay, so this is kind of sad. Like I wasn't able to talk people into like moving significant pieces because of this huge overhead that we had to pay. Okay, so back then we had like kind of this cute bird, and then we fast forward like 6 months, or 6 years, and the bird's changed a little bit, shape's a little different. But what's really changed is we have this enormous gorilla in the room, and that's machine learning. And so all of a sudden, like people said, like, this is what's really important, right? Like, this is something we absolutely have to run, and we're gonna put it on the GPU because it runs really, really well on the GPU, and it's worth doing this move. So it's a really different world than we had 6 years before. And so now everybody's got GPUs in the data center. And so what this has meant is that people are really thinking hard about how do we put everything on the GPU, okay? And now Twitter is a giant hellscape. But beyond that, like all the things we want to do on graphs, even if they're not very good, they're interesting to put on the GPU, okay? Like it can just be on par in terms of performance because nobody wants to move things back to the CPU. So there's a huge investment in sort of infrastructure to do more and more stuff on the GPU because everybody has these data science or machine learning pipelines where something on the GPU is really the cornerstone of that pipeline.
Can I just ask, how about energy consumption? I mean, we live in a world where we worry about energy, and if you give me so many threads and they somehow try to all stay active and they don't do anything useful, it's very sad for the environment.
Yeah, okay, so energy consumption. I think if you look at energy per op, GPUs do pretty well. And the reason is CPUs are not very energy friendly in the sense that all the stuff that you have that you're paying for, there's this incredible, huge bunch of control hardware that doesn't do math, right? You've got this out of order engine all the time that's like moving things around. If you look at a CPU die, most of it is not compute. If you look at a GPU die, a lot more of it is compute. And I would bet if we ran the numbers, and I can find you the numbers because I know who does the numbers, in terms of workloads, because GPUs are so much more compute in terms of where they're spending their energy, it's better energy per die, or per op.
Also, if you don't make much use of the parallelism.
Well, I mean, but you're not going to use the GPU in a way that doesn't make good use of the parallelism. So I'm assuming it's a workload that would be parallel friendly. Okay. So I wouldn't be too nervous about your concern there. Okay. So now we'll actually talk about graphs a little bit. And so academic graph work, I just want to tell you what we do. Most academic graph work only looks at 6 applications, and they're really basic applications, and there's very little compute in there. It's mostly about like traversal-ish kinds of things. And these are interesting, okay? But they are not the things that people are generally running in data centers, except evidently for PageRank, which Google seems to take really seriously. But I would say these are things, you know, if you want to run a general graph workload, you need to be able to run these well, but it is not the only condition because people are running things that are more complicated. In general, GPU graph work, at least in the academic sense, is not particularly programmable. Most things that are released sort of do these 6 and nothing more. They're usually started with like, I have one fast implementation, then I add a bunch of knobs to it, okay, so that I can like put in some different command line parameters. And just to tell you what those knobs are, because that's kind of interesting, the kind of stuff that we think about that influences how fast things run. Load balancing strategies are really important. Okay, so you have lots of fine-grained load imbalance, and you need to keep these SIMD units busy. So you do a lot of moving around of work to try to get regular computation, even though the input is kind of irregular. So load balancing is a big focus. Are you traversing forward or backward? We look at a lot of strategies that are like, it's cheap to do this poorly, and it's expensive to do this well. Okay, filtering, for instance. Well, we could do it exactly, but that's expensive. But we could do a crummy job of filtering. We can do a crummy job of uniquifying. Okay. What do our intermediate data representations look like? Are they dense? Are they sparse? Are they bitmaps? Right? So these are the kind of decisions that we think about. And I think there's a lot of opportunity to do a more systematic exploration of this space because I think there's a lot of things missing.
When you say crummy job, do you mean like approximate?
Yes.
Is it like provably, I mean, you're doing something that you know is going to be a good approximation, or it doesn't matter, or?
So what does a crummy job mean? Okay, so uniquify, for instance, right? So you do an advance and you're looking at all your neighbors, and you've got you know, multiple vertices that connect to the same vertex, and so that's coming out. And you come out with an output frontier. Okay, you could make that perfectly, you know, uniquified. There's probably another name for that.
It just means
to remove the duplicates. Okay, to turn it from a list into a set. Okay. or I can do a kind of bad job and leave some duplicates in there. And that's going to mean I do a little more work down the road because now I've got a few extra vertices sitting in there. But if I do a really cheap uniquify, maybe that makes sense.
Okay.
Okay. We worked with DARPA for a few years. We wrote and so they had very, very different kinds of applications. And so we find these more representative, or we understand these are more representative of like what people actually run in the real world. And they're very different than like do a BFS or single source shortest path. So for instance, just one I want to mention, seeded graph matching, right? So the problem they have is we're going to give you this social graph and it's going to be labeled with things that we know. And we're going to give you this different social graph and it's totally unlabeled. And we think that some of the nodes here correspond with some of the nodes here. Tell us which ones. Okay, there's obviously national security implications that come with that, but that's not single source shortest path. Like it's a much more complicated kind of thing. In general, what we found when we looked at DARPA workloads, what surprised me was how fine-grained they were in terms of like do small parts of a graph application, just do a graph operation, and then do some other kind of compute. Okay, whether it be linear algebra or machine learning or optimization or something like that, and then go back and do graph. They were really fine-grained. Okay, and then what does NVIDIA do? Okay, so NVIDIA has an ecosystem for doing graph work. It's called Rapids. It's in a bigger ecosystem that is for data science. And so they have big, long pipelines that people set up, right? So, you know, I gather in all this data. I do some like pandas kind of processing on it. I output some sort of graph. I do some graph processing. I output it to a visualization engine and so on. So graph is just a piece of this. So what they've really thought about is like, how do we move things from piece to piece? How do we make them modular? What are the data structures? So their primary data structure is a data frame, okay? So like this big tabular, you know, something you'd get out of a database, okay? What they do all their graph computation on is CSR. They don't have anything that's dynamic graph today at all. What they are interested in more than anything else is GNNs, graph neural networks. Like that's what their customers are asking for. They are interested in moving into dynamic stuff there, but they haven't got there yet. So this is pretty simple. Like we have a lot of people that come up with these cool new, brand new data structures, and that's just not practical in this sort of workflow, especially because you don't get any chance to pre-process in this workflow. When you see a graph, you're seeing it for the very first time because it's been dynamically generated right before it gets to you. Okay. So now I want to tell you a little bit about dynamic data structures in general and what we've learned from doing this over the last few years. And the big problem that we have is this real chicken and egg problem, right? There's no applications out there that use mutable dynamic GPU data structures because nobody built them before. And so when we design a cool new data structure or implement something that's been done before, we have literally nothing to plug it into to say like, how's it actually going to work in practice? And so then it just goes around, well, nobody's going to build these data structures because there's no use for them, and then nobody's going to build applications with them. All right. So NVIDIA's just started building a collections library, and all it has is set, map, and multi-map, and they're thinking about a dynamic map. Right. So we're way behind where you are in terms of actually implementing these things in production. And this is where you're going to get really, really creeped out as theorists. A lot of times we compare against the data structure. You have all these beautiful data structures. What we compare against a lot is sorted arrays, right? And that creeps you out, rightfully so. But sorted arrays are pretty good because you can do queries on them. You can do, you know, range queries on them. You know, a binary search is not terrible on a GPU. You have lots of binary searches running in parallel. And then when you mutate these arrays, you get to use GPU primitives that are really fast, sorts and merges. Right? We're really good at doing sorts and merges. So sorted arrays are not terrible. Sorry about that. Something that has come up a lot is this idea of incremental updates, like this week. So the problem is, for us to have good dynamic data structures, we're kind of in this Goldilocks problem, which is if we're making these really small changes to a graph, okay, it's a terrible thing for the GPU because you're like adding 5 things and you need 300,000 threads. So that's not very interesting for us. If we have really big changes, then we just rebuild the data structure from scratch, right? And we're pretty good at bulk build. Okay, we know how to do that. All that's often an interesting problem. The question is like, where are we in the middle here? Like, do real applications use, oh, I want to throw in 100,000 vertices at a time or changes? Okay, and because of this problem, we're not really sure in practice, right? This is very much if we build it, hopefully they're going to come, but it concerns us. Okay, and we run the experiments and we say, like, when does the crossover, when does it make sense to bulk build versus doing this incremental sort of thing as a function of batch size and so on. And these are exactly the sort of things we've been talking about all week, and we worry about that too. I'll skip a few things here, but I also wanted to get to semantics because this came up as well. So what do programmers really want when you start to work in this parallel world? So it's really easy to say, hey, I've got this dynamic data structure and I have this list of changes and we're going to apply them one at a time. And there's this deterministic thing that's going to come out when you apply them one at a time. Okay? What happens if you give a batch of updates at a time? What does the programmer expect when that happens? Does the programmer expect that they're going to go in order? Okay. Well, we could do that, but it would take an enormous amount of work because we need to serialize it, or at least go to a lot of work to figure out what we can do in parallel. And so we kind of think that maybe bulk semantics are interesting. Okay, the idea of I'm going to throw this in here, it's going to be consistent, but I can't make you any promises about what order they're going to happen. And then the question is, what happens when I do additions and deletions and changes to pieces of data? What can you expect when that ends up happening? The other thing that we're curious about is, again, with real applications, are they phased? Are they phased in the sense of, is there an update phase, and then we stop mutating the data structure, and then we query it, and we only query it when we're not updating it? I'd say my instinct is most applications are phased, and that makes our problem a little bit easier, okay? Because we don't have to worry about like making queries while we're in some sort of inconsistent state. But this is an unanswered question, for me anyway. Okay, so now I'm like 50 minutes in. So let me tell you about 4 different things that we have done as a community to actually do graph data structures. And I will get through this in just a few minutes because they're not very complicated, and that's why they're going to probably make you feel a little bit queasy. So what we start with is CSR. Okay, we got this list of vertices. Each vertex has a bunch of neighbors. We pack those neighbors together into a dense array. Awesome. Obviously, this is really hard to update because you stick in something here, you got to move a lot of things over. So the first thing we can do is we can say, let's split those up. Okay, and this was done in a Georgia Tech project called Hornet. And so each one of these is now an individual data structure. And we keep all of our elements in here. And if we want to put too many elements into there, then we stop, we double the size of what's there, we copy things over and continue. Okay? So that's one thing that we can choose to do. Another thing we can choose to do, and this is work from TU Graz in Austria, and really great group over there. I really like the work that they do. And they say rather than having sort of these arbitrary size things that keep doubling in size, we're going to instead have these fixed size atoms and then have a linked list of those. And if we need more, then we'll just sort of append something else on the end. So you know better than I do sort of what the trade-offs are between these two things. One nice thing is you don't have to copy if you're adding a bunch of new things, but they're both different ways to think about organizing practically a data structure. And these both work, which is great.
Are there benefits to having a fixed block size?
Huge advantages to having a fixed block size, and I have slides on that I'm not going to really be able to cover. The block size that you want, and this is really the key of our hash tables that we have built, is the size of a warp. Right? So, and then we have an entire warp making operations on the hash table at time. So our warps are like 32 big, and so we have like a 128 byte atom, and that's what this group has also chosen to do. Okay, so the design choice that you have to make here is what do you actually store in each of these data structures, whether it be organized like this or not. And so this is where this becomes very challenging because the question is, do I store a sorted list or do I store an unsorted list? Okay. If I store an unsorted list, then queries to say, is there something in the list are very expensive because you have to walk the whole list. Okay. If I store a sorted list, I can do a nice little binary search and that's faster. On the other hand, I have to maintain the list. Okay. Both of those things are undesirable and expensive, and it kind of depends on what your workloads are. Are you doing more queries or are you doing more updates as to which one's going to make more sense? But both of those are relatively expensive. So we tried to avoid that. So ours is the third way we did this. We said instead of using lists to represent things, we're instead going to use hash tables. And so we're going to have a list of vertices, and then each vertex has its own hash table that stores all of its neighbors. And you know how hash tables work, and you know what the advantages and disadvantages are. And so we have previously done work that is building fast dynamic hash tables, and we do it by having atoms that are a particular size that are well suited to the GPU, but these are hash tables that are pretty close in performance to the best static hash tables, which is kind of nice. Okay. We think as we get large vertex adjacency lists, then B-trees might make sense, and we've done work in that too, but that's just a ton of engineering to put together. I have details on the hash table, not going to really cover that right now, but what we, one of the contributions we made here is to start thinking about how do you evaluate these? Because again, we don't have dynamic graph applications on the GPU, and it was nice to hear about some of the ways you guys are generating dynamic graphs. For instance, taking something with temporal and then sort of walking through time. Like, that makes a lot of sense. We were a little lost in terms of what these data structures could be. Sandia has a benchmark called Firehose, I think, and that seemed interesting. But in general, we need to know as a community more about these data structures. Guy Blelick sort of talked about his different models for what these should look like. We thought about sort of individual benchmarks on low-level stuff. We thought about how you do global builds, and then we thought about applications, and we sort of talked about what each of these levels should have in terms of evaluations. You know, DARPA, for instance, was saying one of the scenarios we should think about, they called it add and age. So they said, basically what we want is like a fixed size data set that you're changing over time. You keep throwing new things in, but every time you throw new things in, you get rid of the oldest things. Okay, and that was consistent with one of the things that Guy said in his talk on Monday. Okay, cool. So one of the benefits of this is it's just much faster to build. It's a lot faster to build hash tables than it is to do that sorting problem of basically sorting each one of these things individually. You do this big segmented sort, but it's much faster for us to build our hash tables. And so that was a win in terms of what we were trying to do. The last data structure that's been done is like an early access paper on IEEE TKDE right now, which is something we heard about in the last couple of days, building a packed memory array. This is an enormous engineering effort to make this work on the GPU. But it's a nice data structure for this, right? The theoretical bounds, as I understand them, are favorable for some of the operations that we'd really like to be able to do. What they hung their hat on in terms of performance was what they called a sorted neighbor query. They felt that it was important to be able to ask the data structure to give you the neighbors for any particular vertex, and that be sorted. And I'm a little skeptical because I don't know applications that require sorting. Okay, if you give it to me and it's unsorted, I'm cool with that. I mean, there might be some locality reasons, but obviously a PMA is going to give you something sorted, whereas a hash table will not. Anyway, there's some good work on doing PMAs that's pretty recent, and I think I'm excited to see more work in this direction. Okay, so what I think is important for what comes next, like for our community, we need to understand workloads better, and I don't think we've done a really good job of that. I'm interested in just building more data structures, and I kind of look and say, these seem cool, and maybe they would be great on the GPU. I think persistent data structures are neat, and I think a lot of the data structures that are used in some of the functional programming literature are also neat, but I don't know if they're a great fit now, but I would be excited to learn more about them. I would love to hear data structures from you. One of the worries we have is like, are the APIs that we have like the right kind of APIs? And so if we have a higher level language than CUDA, maybe we kind of hide that and we can build something that works very nicely within a particular language where we can hide the details of like how we actually access it, and then be able to build languages that have good data structures underneath them. And the other thing we're looking into is a lot of these data structure problems sort of involve maintenance of some kind, doing garbage collection or deleting all the tombstones or rebalancing or whatever. And so we're thinking about GPU runtimes that might be able to sort of do that alongside other data structure kind of applications. Thank you.
Thank you so much for a great talk. Any question?
I mean, this is very philosophical now, but so I'd like to understand also in terms of community, what do you think is the difference between algorithms engineering and systems engineering?
Yeah, so the stuff that I'm talking about here, I would call that algorithm engineering, right? The kind of papers we've written on data structures, I think it's the right kind of fit. I think when we are building something that doesn't involve interesting or novel ways to think about data structures and algorithms, maybe then it gets to a little bit more systems. But I think the stuff I've talked about today, I put it in that category.
Good.
And that's worked for us in terms of publication strategy as well. Like there's a community that's interested in this kind of work and understands we're not doing new algorithms. We're maybe thinking about how do they map best and how do we make them run fast.
What's a conference for that community? So something like that.
So like I like to go to parallel computing kinds of things. So like PPOP or IPDPS are really good parallel computing conferences that have interest in algorithmic engineering. And like IPDPS has specifically, I think, a track that is algorithmic engineering. I'm trying to think where else we've done, like an Alinix kind of thing. And then we had a paper last year, like a hash table paper that was in, I don't even know the name. It was in Italy in like January. Some of you went, probably. No one knows.
APOX?
That's right, APOX. So like that seemed like a good fit too.
And so which communities do you reach in these conferences? Because, I mean, Linux is sort of more typically internal to the algorithms community.
Yeah.
But if you actually are more interested in telling the rest of the world, here's actually an algorithm that's useful.
So if
you
it's
wanna have that
more
kind of
with a
reach.
systems focus, then I'm going to go to a more parallel computing conference like a PPOP or an IPDPS or something like that, supercomputing. I will say that one of the weird things about the GPU community is we don't really have a home. Okay, there isn't like, this is where we do all the best GPU work, and that's both good and bad. It's good because it's bad because like you always have to convince people like, hey, we're part of your community. It is good because you're publishing in a lot of different places, and so it gets you perhaps a broader audience.
So if as an algorithm person, I want to do research that is helpful for you, what would you suggest? I mean, it's the first thing to think about a model, even though it might be very complicated, that you approve of, and then start to think of, no, it makes no sense if you don't think it makes sense. And then start thinking of developing algorithms in that direction for that model, or how would one go about?
Yeah, I think I would start, like, we have done well with theorists saying, hey, you don't have these at all. And here's this cool thing we've thought of that seems to be parallel friendly. And, you know, we have huge missing chunks out of the space of what we've implemented. Like hash tables seem like a useful thing to have. Okay, how do we think about it? What is the kind of formulation that makes sense? Like here's all these things, but like cuckoo hashing, that seems to have some good properties. Can we map that well? And so it's sort of like, where are the holes? But it's a lot of times people saying, hey, there's this recent work in this that I did or that I know about in this community that actually seems to be practical. And people have done interesting implementations, or just the bounds are good and it's really parallel friendly. Is this something that would seem like it would be something to do on the GPU? I think things that work, the parallelism I think is the hard part, right? So a lot of PRAM algorithms map well, but it doesn't really have any conception of locality. And that makes things a little bit tough. And so I think there's more advanced models that take that into account. But starting with something that's parallel friendly is by far the most important thing. Does that answer your question?
Any more questions?
Right.
Okay, let's thank John again. Thanks a lot.